We now close the loop and talk about molecular geometry, especially as it's related to the VSEPR model geometry that we learned about last time. Our learning goals are to be able to distinguish the electron cloud geometry predicted by VSEPR model with molecular geometry, which is a subset of that. So let's review those electron pair geometries. If there are two electron clouds around a central atom, then the corresponding geometry or shape is linear. If there are three, then it is something we call trigonal planar. That is, the three atoms are distributed with angle of 120 degrees between them. If there are four, then it forms a shape that we call tetrahedral because the four outer atoms are all forming the vertices of a tetrahedron. So now, how does this contrast with molecular geometry? Well, remember the VSEPR model guides the shape of electron clouds around a central atom. Those electron clouds could be in the form of sigma bonds around that central atom. And the molecular geometry itself is defined by where the atoms are. So if those are three sigma bonds, then this trigonal planar arrangement that we've shown here would be the molecular geometry also. But if the central atom has electron pairs, then the VSEPR model isn't strictly speaking equal to the molecular shape. So here's an example. There is a trigonal planar arrangement around the central atom, but one of those is a non-bonding pair of electrons. So the actual positions of the atoms in this molecule is a bent shape because it's a triatomic molecule. Remember, ozone is an example of this. So there are three scenarios that are going to present exceptions for us, and so let's consider each of those. Okay, the one we've just looked at is trigonal planar with one lone pair. Okay, another example besides ozone is sulfur dioxide, and it looks something like this. So you can see that the molecule is bent with a three-atom shape, but it has an extra lone pair on the sulfur, and that's what causes this to be bent instead of linear. Another possibility would be we have a tetrahedral electron cloud, but there is one lone pair. A good example of this is ammonia, and this indeed has a shape that is not trigonal planar, but is trigonal pyramidal because of that extra lone pair of electrons that occupies one of the four spots around the nitrogen atom. Finally, we could have a tetrahedral electron cloud with two lone pairs, and a good example of this is water. All right, water looks like this, and you can see that it is not linear, it is bent because it has two lone pairs of electrons on the oxygen. So the four electron clouds around oxygen form a tetrahedral shape, but only two of those are actually occupied by hydrogen atoms. So now I want you to try one. I want you to try to find the molecular geometry that you would expect for phosphorus trifluoride. All right, I'm going to give you a chance, take a pause on the video to try to work this out. The four steps that you need to follow are shown below. Okay, how did you do? Well, if you drew the correct Lewis structure, you should have come up with something like this, where you've got three single bonds between phosphorus and fluorine and an extra pair of non-bonding electrons on the phosphorus. The number of electron clouds, 3 bonds plus one lone pair, is equal to 4. So the electron cloud geometry from the VSEPR model should be tetrahedral, and the fact that one of those is a non-bonding pair of electrons means that the molecule has a trigonal pyramidal shape, just like ammonia did. And this is what it would look like. So there's a few mistakes you want to avoid when you're finding molecular geometries. One, please start with the correct Lewis structure for the molecule, including the correct number of valence electrons. If you get this wrong, you'll never get the molecular shape correct. You always want to assign the VSEPR shape based on the total number of electron clouds. That is the total number of bonds plus number of pairs of non-bonding electrons. Each pair constitutes another electron cloud. Finally, account for those non-bonding electrons on the central atom and assign the molecular geometry based purely on the locations of the atoms around it. I hope this made sense and that you'll be able to find molecular geometries of your own within short time.